Assalamu alaikum dear students. In the last lecture we had derived an equation that we called as steady flow energy equation. If you recall, the equation was like this: h1 plus v1 square by 2 plus gz1 plus q is equal to h2 plus v2 square by 2 plus gz2 plus ws. So we know that here h1 is the enthalpy of fluid at the inlet, v1 is the velocity of fluid at the inlet, z1 is the elevation of inlet section from the datum, Q is the heat input into the system, H2 is the enthalpy of fluid at the outlet, V2 is the velocity of fluid at the outlet, Z2 is the elevation of outlet section from the datum, and Ws is the shaft work or mechanical work produced during the process. Now we will see the applications of this steady flow energy equation. There are many engineering applications of the steady flow energy equation. Some of the applications are in mechanical power generation or power plants. Second is in steam turbines, in compressors, in heat exchangers, in steam generators, in nozzles, and there are many other applications of steady flow energy equation. When we are talking about the applications of steady flow energy equation, mathematically we have to relate the heat input or the mechanical work to the enthalpies or velocities or the elevations in this case. Some of the important application areas of steady flow energy equation we will be dealing with are here discussed as: first is nozzles and diffusers, second steam generators or boilers, steam or gas turbines, compressors, throttling devices, and centrifugal pumps. Now, first application we'll be dealing with is a nozzle and a diffuser. A nozzle is simply a device that is used for increasing the velocity of fluid at the expense of its pressure drop. Actually, a nozzle is having less cross-sectional area at the inlet section, and the area of cross-section increases towards the outlet section. Actually, when the fluid passes through a nozzle, the pressure of the fluid or the enthalpy of the fluid drops, due to which the fluid is accelerated from the entry to the exit of the nozzle. Now we are having some correct features of fluid when it is going inside a nozzle. Firstly, there is no shaft, so the shaft work or mechanical work here will be zero, or we will say that this Ws quantity will be zero. Second, the walls of this nozzle are thermally insulated, or we can say that the flow is adiabatic. There is no quantity of heat input into the system, so this Q will also be zero. Third, the nozzle is fixed at one place, so the change in elevations from the datum are zero, or we can say this Z1 minus Z2 is equal to 0. Now with these stipulations, the steady flow energy equation, the quantities like this Zg1 will be 0, Q will be 0, here Zg2 will be 0, also Ws will be 0. So we'll be remaining with certain quantities. These are this H1 plus V1 square by 2 is equal to H2 plus V2 square by 2, or we can say V2 square minus V1 square by 2 is equal to H1 minus H2. So you can see that there is increase in the kinetic energy of fluid or increase in the velocity of fluid from V1 to V2 at the expense of decrease in the enthalpy of the system, or we can say the enthalpy in turn depends upon the pressure, because we know that H is equal to U plus PV, so there is decrease in pressure. Because of that, the velocity of fluid increases. Now using the continuity equation, we know that M is equal to A1V1 by V1 is equal to A2V2 by V2, where A1V1 and A2V2 are areas of cross section at inlet and outlet, velocities of fluid at inlet and outlet respectively, and small v1 and v2 are specific volumes of fluid at inlet and outlet respectively. Getting V1 from this equation, we can have V1 square is equal to V2 square multiplied by A2 V1 divided by A1 V2 whole square. Using this value of V1 in this above equation, we have V2 square minus V2 square multiplied by A2 V1 divided by A1 V2 whole square is equal to twice H1 minus H2. Upon further simplification, we can get the value of V2 that is required for calculations, or the value of exit velocity, as under root of 1 upon 1 minus A2 V1 divided by A1 V2 whole square into under root of twice H1 minus H2. Now, if we know all these values, we can get the value of this exit velocity. But it is found that the inlet velocity, or the velocity of approach V1, is very small as compared to the velocity exit velocity, or velocity V2. So if we neglify the value of V1 in this equation, we can get V2 square is equal to twice H1 minus H2, or simply V2 is equal to under root of twice H1 minus H2. So simply we can see that the velocity of fluid is increased at the expense of decrease in the enthalpy of the system. If we know the values of enthalpies, we can calculate the value of velocity. Now another case is that is of a diffuser. A diffuser is simply the reverse of that of a nozzle. In a diffuser, the velocity of fluid is reduced at the expense of increase in the pressure energy, or we can say the pressure energy or the enthalpy of the fluid increases at the expense of velocities. Here we have, when the fluid is subsonic, the cross-section area of the diffusing duct diverges from entry to exit, and when the fluid is in supersonic speed, the cross-section area of diffusing duct decreases from entry to exit. Here we will not deal with the supersonic and subsonic speeds because it's a different topic. You have to only remember that a diffuser is simply the reverse of a nozzle. Only here the velocity of the fluid decreases, or we can say the pressure increases at the expense of decrease in the velocity. The second case we are having is steam generators or boilers. A boiler is an equipment that is used for the production of steam, so these are also called as steam generators. Here the thermal energy of fuel is used for converting water into steam. Then that steam is used for different purposes. It is used for doing mechanical work in steam engines or steam turbines. It's also used for heating residential or industrial buildings. It's also used in chemical sector or the textile sector. Now we will see the characteristic features of the fluid flowing through a boiler. Firstly, there is no shaft, so this quantity Ws will be 0 because there is no production of mechanical work or shaft work. Second, it is seen that there is not much change in the velocities of fluid when it is going through the boiler. So there is no change in kinetic energies. V2 square minus V1 square by 2 will be equal to 0. Also, the boiler is fixed at one place, so the change in the elevation Z1 minus Z2 will also be 0. Now, with these stipulations, the steady flow energy equation reduces to this quantity V1 square by 2 will be 0, Zg1 will be 0, here V2 square by 2 will be 0, QZ2 will be 0, plus this Ws will be also 0 because there is no production of mechanical work. Now the equation remains here, that will be mH1 plus Q is equal to mH2, or we can say Q is equal to m into H2 minus H1. So we will see that the quantity of heat given to the water for converting into steam is used for increasing the enthalpy of the fluid from H1 to H2. So the enthalpy of the fluid increases, what we will get, that will be the steam with increased enthalpy. Now, another application we are having is a steam turbine or a gas turbine. The difference between a steam turbine and a gas turbine is simply that in a steam turbine, the working fluid is steam that is produced from hot water, and in a gas turbine, the working fluids are different combustible gases, or it can also be air. In a turbine, simply the fluid with higher pressure energy goes inside the turbine, and inside the turbine it expands from higher pressure energy to a lower pressure energy. Due to this, the shaft inside the turbine rotates, and that output can be used for generation of electricity through the electric generator, or it can also be used for other purposes. Now we will see the characteristic features of fluid that is going inside the turbine. Firstly, we will see that the velocity changes are negligible here, so there will be no change in kinetic energy. Second, the potential energy changes are also negligible, so Z1 minus Z2 will be 0. Also, there is no transfer of heat into the turbine because the walls of this turbine are thermally insulated. So the quantities V1 square by 2 will be 0, Zg1 will be 0 here, Q will also be 0 because there is no heat input. Here V2 square by 2 will be 0, Zg2 will be 0. So we will remain with mH1 is equal to mH2 plus Ws, or keeping the Ws here, we will get Ws equal to m into H1 minus H2. So simply we can see that work is done at the expense of decrease in the enthalpy of the system, or we can see that the decrease in pressure actually caused the decrease in enthalpies. So at the expense of that decrease in the enthalpies, work is done by the turbine that can be used for different purposes. Now another thing we are having is compressors. Compressors may be of a rotary type or a reciprocating type. We will not explain the types of compressors here. You will simply remember that a compressor is a device where mechanical energy is used for increasing the pressure and temperature of a working fluid. In a compressor, a motor is driving a shaft, and that shaft in turn increases the pressure and temperature of a working fluid inside a compressor. That working fluid is used for different purposes then. So inside a compressor, the fluid is having certain characteristics. First of all, there will be shaft work because the shaft is doing work on the fluid inside the compressor. But as the work is done by the surroundings on the system, so here W will be negative, as we have already seen this. Also, the potential energy change will be 0 because the compressor is fixed from the datum, so Z1 minus Z2 will be 0. But when the fluid is going out of the compressor, it will be having some temperature. So actually heat is given out by the system to the surroundings. So this Q, we know that when there is outflow of heat, that is negative, Q will be negative. Also there will be some velocity change because the pressure of the fluid is increasing, so there will be velocity change also. With these stipulations, we can write the steady flow energy equation as m into h1 plus v1 square by 2 minus q, because it is outflow of heat from the system to the surroundings, is equal to m into h2 plus v2 square by 2 minus ws because work is done by the surroundings on the system. So Ws will be equal to m into h2 plus v2 square by 2 minus m into h1 plus v1 square by 2 plus q. If we know all other quantities, we can get the work output or work input we are giving to the system or to this compressor. Now, if we neglect the change in the velocities, however, these are not negligible, but if we neglect the velocity changes and we treat that the system is adiabatic or Q is also equal to 0, then we will get simply Ws is equal to m into h2 minus h1. That means that the work that is transferred to the system or to the compressor is actually used for increasing the enthalpy of the system or increasing the pressure and temperature of the system, the working fluid. We will see that it's actually reverse of that of turbine. In the turbine, the enthalpies by decreasing and giving the output work. Here the work is used for increasing the enthalpy. So compressor and a turbine, these are actually reverse case of each other. Now another application we are having is a throttling device. A throttling device simply is that when a fluid flows through a constricted passage or a partially opened valve, a simple gate valve we are having at homes, when it is partially opened, this will become a throttling device. So when the fluid is flowing through a throttling device, the features it is having that firstly there is no heat input, so we will be having this dq by dm, or simply q is equal to 0. Also there is no production of mechanical work, so ws will be also 0. Potential energy changes are also 0 so z1 minus z2, that will be also 0. So the quantities these gz1 plus q and here gz2 plus ws, they will become 0. We'll be remaining with h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. So if you see the figure or the picture of this throttling device, you will see that fluid is flowing inside the throttling device, and this is partially open, so the pressure energy of this fluid is decreasing. This is the flow through value. Usually we also ignore the potential energy, these kinetic energy changes also, because the velocities of the fluid usually does not change much. The velocity remains like constant, so we can say that this equation reduces further to h1 is equal to h2, but simply we will see that the enthalpies of the fluid inside a throttling device remain constant. The enthalpies of the fluid does not change much inside a throttling device. The last thing remaining is a centrifugal pump. A centrifugal pump is a device that uses mechanical energy to lift water from a lower level to a higher level, thus increasing its potential and energy. So in a centrifugal pump, the characteristics of the fluid are that there is no heat input into the system or into the pump, so this quantity Q will be 0. Also, there is no change in temperature of the fluid, so we'll be having this, there is no change in potential energy because the temperature remains constant. But the quantity H is not used here because we know that H is equal to U plus PV. U is 0, but PV is not 0 here, so we'll write the equation accordingly. Also, the work is done by the surroundings on the system, so it will be negative. So we will write the steady flow energy equation as m into PV P1 V1. Here I'm not writing H1 because the quantity U is 0 in that, so m into P1 V1 plus V1 square by 2 plus GZ1 is equal to m into P2 V2 plus V2 square by 2 plus GZ2 minus W. So if we know all other quantities, we can get the amount of work required to lift the water from a lower level to higher level. This is the case of a centrifugal pump.